Okay, this is a walkthrough of a problem where I'm going to combine two skills for Newton's second law. It's going to be a rolling and sliding problem, and I'm going to use an inclined surface. So we're going to have to deal with a rotated coordinate system. And it's going to be two bodies in contact that have the same acceleration. So we're going to have to do both of those two things. Okay, so here's the problem we're going to do. So let's say that this is the incline. It's at an angle of 10 degrees with the horizontal. And there are two carts on this incline. And they're connected by a cable. Let's say that this one is 10 kilograms and this one is 5 kilograms. And there's a force of 40 newtons applied that way. And we don't know what's applying that force. It could be a cable or whatever. And we want to know, first, what's the acceleration vector? And I could be asking that about either one of these two bodies because their accelerations are going to be the same. And then second, what's the cable tension between the two bodies? That's actually a really useful thing to calculate in engineering type problems because the cable tension is going to tell you how strong a cable you have to have there, or if the cable that you have, if you have to be worried about it breaking. Okay, well, the first thing we have to do in a problem like this, any rolling and sliding problem, is we have to choose our coordinate system. And the coordinate system we choose is going to determine how the weight force vectors act, you know, the angle that the weight force vector acts at in your coordinate system. So pause the video for a second and figure out what coordinate system we're going to use and what the angle is that we're going to want for our weight force vectors. Okay, well, the coordinate system is always going to have, on any rolling and sliding problem, is going to have the y-axis pointing out of the surface and the x-axis pointed along the surface. And so if I draw the coordinate system here, any weight force vectors are going to be, you know, they obviously act straight down. And this is the 270-degree line there. And this angle is going to be the angle that the incline makes with the horizontal. Okay? So the angle that we want for our weight force vectors is going to go from the positive x-axis all the way around to the weight force. And that angle in this case then is, we get to 270 and we go past it by 10 degrees, so this is 280 degrees. So any weight force vector is going to be the weight of the object times cosine and sine of 280 degrees. Okay, now that we've done that, what are we going to isolate? There's a strategy that we always use in these problems where we're isolating the two things together, where their accelerations are going to be the same. So what are we going to isolate? What we're going to isolate first is the entire system. So in this case, both of those two objects together. So a free body diagram of the whole system. You don't have to be this careful with your outlines, but I'm just trying to be clear about what I'm looking at. Okay, and what forces are acting. There's the weight force. The whole thing has a mass of 15 kilograms. So the weight force is 15 times 9.81, so 147.15. Then there is the applied force of 40 there. And then there's the only place where the surroundings make contact with this system is where the incline touches the wheels. And I'm going to call this N total. You know, that's just a variable name, but I'm going to use different N's later, so I just am trying to be clear about that. Okay, so now we go to Newton's second law. And we're just putting in these vectors. The 40 in our rotated coordinate system is in the negative x direction, so we have negative 40, 0. The n is in the positive y direction, so 0 n total. The weight force, we already figured out, is at this angle of 280 degrees. So this is 147.15 times the cosine of 280 degrees. And 147.15 times the sine of 280 degrees. We'll calculate that in a second. Three forces in the free body diagram. We have the three forces, so that's everything on the left side. And now this is equal to the mass times the acceleration. The mass of what we're isolating is 15. Now, what's the acceleration? You have to think, is this moving along the x direction or in the y direction? And you don't have to worry about plus or minus. That'll come out in the math on its own. So think for a second, do we want x or y? This is going to move along the x direction. So we're going to write this down like that. And I guess I'll calculate this weight force vector and rewrite this equation. So this comes out to be negative 40, 0 plus 0 n total plus 25.55 negative 144.91. And if you didn't get that, your calculator might be in radians. And that's equal to 15 times A0. Okay, well, what we're looking for is the acceleration vector. And all we need in order to come up with the acceleration vector is that variable A. And that means that the only equation we need here is the x equation. So negative 40 plus 0 plus 25.55 is equal to 15a. And so you get negative 14.45 is equal to 15a. And so a is equal to negative 0.96, I'll just leave it like that, meters per second squared. Okay, that's not the acceleration vector, that's just the variable a. So now, pause the video for a second and come up with the acceleration a, the acceleration vector, given this value a. Okay, so now we're going to plug this value a back into the vector that's in the green dotted circle. And our acceleration vector is negative 0.960. Another way you can think of that is it's in the negative x direction of our coordinate system that we chose, so it's this way, with a magnitude of 0.96 meters per second squared. Okay, so that's part A. Now the second part is we want to calculate this cable tension. So just think for a second, how are we going to do that? What are we going to isolate now? The answer is, in this case, we can isolate either one of those two individual carts to get that. Which one do I want to do? It's a little funny when you first start doing this to realize that if you isolate the 5 kilogram cart, that 40 doesn't even show up in your free body diagram, and yet somehow you come up with the same tension in that cable either way. Like, how does the math know that that 40 Newton force is even there if you isolate the 5 kilogram? Well, the answer is it's baked in through the acceleration, which is what we're going to use. So I'm going to do it that way. I'm going to isolate the 5 kilogram. We're going to calculate that cable tension that way. But if you want a little extra practice, isolate the 10 kilogram also. You need to get the same value of T that way if you did it right. Okay, so now I'm going to go free body diagram of the 5 kilogram. There's a weight force of 5 times 9.81. There's a pushing force from the ground. I'll call that N5. That's why I use this N total before as my variable, because it's not going to be the same as this N, so I'm just making those different variables. And then there's one other place where the surroundings make contact with the 5 kilogram thing. That's at that cable connection. So pause the video for a second and put that cable force in your free body diagram. Okay, so that's a pulling force. That means the force is parallel to the cable away from the body. And I'll give it the name T. And that's all the forces. So now we'll go to Newton's second law. That T force is in the negative x direction. The N force is in the positive y direction. This weight force, again, we're going to use the angle 280. So this is 49.05 times cosine of 280. And 49.05 times the sine of 280. That's all the forces. Now pause the video and put in the right side of Newton's second law. What we get there is the mass of our chosen body times the acceleration that we just calculated. So this is times 0.960. That's why we needed that acceleration vector first. And even if I wouldn't have asked for it, in this problem I asked for it as part A, but whether I ask for it or not, that has to be the first step in problems like this because it has to show up there. Okay, so let me rewrite this Newton's second law equation. So we get negative T0 plus 0 N5 plus 8.52 for the x component and negative 48.30 for the y component. And that's equal to 5 times negative 0.96 Well, what we're looking for in this case is this variable t. So again, all we need is the x equation. So negative t plus 0 plus 8.52 is equal to 5 times negative 0.96. It's actually 0.963 repeating, so I'm going to put that in. So this comes out to be negative 4.82. And so you get negative t is equal to negative 13.34. And so t is equal to positive 13.34 newtons. And the cable tension doesn't have any direction, so this is a good answer on its own. It would be different if I had asked for the force that cable applies, the force vector that cable applies to the two bodies. Then you'd have to think about the direction of that force, okay? And if you're talking about the force the cable applies to the 5 kilogram cart, that force would be in the negative x direction. But if you're just looking for t, then this is the answer. And if I had isolated the 10 kilogram cart instead, I would have gotten this exact same answer for t.